Hello, this video is going to demonstrate our Verdict toolchain. Currently, Verdict can run on Mac OS, Ubuntu, and CentOS. If you are using Docker, you can also run Verdict on Windows machine. Here shows the Verdict manual. Verdict mainly consists of model-based architecture analysis and synthesis, cyber resiliency verification, and also automatic generation of assurance case fragments by leveraging assurance evidence generated by model-based architecture analysis. I will demonstrate each of the features on a delivered drone model. Here shows the delivered drone model written in ADL inside our SATA environment. It has the architecture information, data flows, behavior information, verdict requirement, and also formal properties. The system architecture is also annotated with meta-level properties and defense properties. The meta-level properties are properties like component type, which could be software, hardware, hybrid, and etc. The defense properties are properties like DOS protection, fail-safe, which are an integer range type between 0 and 9. It describes the rigor to implement the defense, which is known as design assurance level, DAO, with 0 being the lowest rigor and 9 being the highest rigor. First, I'm going to show model-based architecture analysis and synthesis. The analysis performs fault tree analysis for safety requirements and the attack defense tree analysis for security requirements. Now, let's first run analysis on the first model, V0. Here shows the results for two mission requirements. Let's focus on mission requirement number 1, which is deliver a package to the intended location. The mission cyber requirements and the safety requirements here are determined and modeled by security experts. And mission requirements number 1 is supported by two cyber requirements. Cyber requirement 0.1 and 0.2, and also one safety requirement. As you can see from the results tab, mission requirement number 1 failed because two cyber requirements failed. The failure of two cyber requirements is because the calculated likelihood of successful attack to the system is greater than the acceptable likelihood. The acceptable likelihood is what the designer set in cyber requirements, which is to ensure the success to deliver a package to the intended location in the mission requirement. When requirements fail, the analysis also returns failure paths as explanations. Let's right-click on the failed requirement and view the failure paths. Each path here corresponds to a minimal cut set of component attack pairs for the system. As you can see here, the likelihood for path number 1 is 1. This is because delivery item mechanism component is susceptible to KPAC 439, which is manipulation during distribution. And there is no defense implemented for that component in the system. In the meanwhile, the analysis also suggests defenses to mitigate the attacks. For KPAC 439, the analysis also suggests defense to mitigate the attacks. It recommends SA12, which is supply chain protection, and also SA18, -1 tamper resistance and detection. Now the user can go ahead and implement those defenses to mitigate the attacks. Alternatively, user may run synthesis to synthesize a minimal set of defense properties with respect to their implementation cost. Now, let's take a look at synthesis. For synthesis, we need to specify costs for all possible combinations of component defense property and the design assurance level. So we offer two ways to do that. One is linear scaling costs, and another one is user customized costs. Here shows the GUI panel for specifying costs. For the demo purpose, we will use the default costs, which is linear scaling cost with a scaling factor 1 for all possible combinations of component, defense property, and DAO. In other words, the cost for component, defense property grows linearly with respect to their DAO. Now, let's run synthesis. Make sure we use implement defenses. By using the implement defenses, we treated the implement defenses as free. We will synthesize a minimal set of new defenses or upgrades to be able to satisfy all cyber requirements while minimizing the total costs. So in this case, the synthesis recommends to implement two defense properties to the DAO level 7. Then the designer can go ahead and implement the defenses. Please note here, the defenses for those properties are still 0. Once the designer implement defense properties in the system, they can apply the recommended changes from synthesis to the ADL project and check again with MBAAS, the analysis. Now let's apply the changes and run analysis again. Please note that here, if you choose to apply the changes, the original ADL project will be saved in another folder called synthesis backup for reference purpose. Now let's clean the projects to clear all the errors. And rerun the analysis. Since we have implemented all the defenses, we expect all the cyber requirements succeed. So now the results are as expected. So additionally, you can rerun synthesis to synthesize a minimal set of defenses with respect to already implemented defense costs. So this time, we will no longer treat the already implemented defenses as free. Let's run synthesis again. So the synthesis will remove unnecessary defenses and downgrade defenses while minimizing the total costs and satisfying all cyber requirements. As you can see here, we have a total cost reduction of 327 unit. if you follow the recommendation listed here. That's my demonstration for model-based architecture analysis and synthesis. Now, let's move to assurance case generation. As I said earlier, Verdict has a capability to automatically generate assurance case fragment using Go structure notation by leveraging the assurance evidence generated from model-based architecture analysis. Now let's run assurance case generation. For the demo, we will generate assurance case fragments using the built-in assurance case patterns for mission requirement 01. So the idea of assurance case generation here is to map the verdict mission level requirements to high level goals in GSN, and the supporting cyber and safety requirements are mapped to lower level goals to support high level goals. The analysis results will be used as solution to support lower level goals. Here shows the GSN graph for mission requirement number 1. The red color branches are the failing branches. The green one is the successful branch. You can also check the evidence by clicking on the solution node. To generate GSN graph, we use a built-in strategy, which is the model-based architecture analysis to substantiate lower level goals. But we also add new fields in Verdict Annex called strategy, context, and justification for user customization. The entire GSN can also be outputted in XML format, which can be easily consumed by other assurance case tools. This is my demo for the assurance case.